moment. Also, okay. Let's have a look at the turbulent kinetic energy. Turbulent kinetic energy describes the amount of momentum inside a cell. Yeah, if you have these big swirls and little swirls, yeah, and we have three different momentum components, then we can here describe this swirls. Yeah. So we have at first our dissipation. Yeah, we have the production of energy. Here it's a green color. The swirls are produced, but after a time they disappear. That always happens in nature. If you have a swirl, if you have a swirling region and a turbulent region, and you do nothing, you just wait a while, then after some time, the swirl dissipates. Yeah, it disappears. Okay, and now you know what the turbulent kinetic energy is. It is some amount of fluctuation, and for this amount of fluctuation, you must always solve a balance. You must always solve an equation, because this energy will be transported through your simulation region. Yeah, you have a rate of increase for your K value. You have a convective transport of your K value. You also will have a diffusion of the K value. Yeah, that happens if you can imagine a jet or a jet of a rocket or an airplane. This K will also diffuse to the sides. Yeah, you will have a rate of production, and you will also have a rate of destruction. So the swirls will be destructed, so the swirls will be destroyed after special after some time. Yeah, you will have this epsilon value. This will disappear. So you have your here. You have your it's getting a bit more problematic. You will always have a fluctuation of the mean values and of the dissipation, of the deviation of the velocity. So you will get some more terms, but I think that's pretty much a bit too difficult for now. And here you see also again the rate of dissipation. You can calculate the dissipation. It's a unit of time. You can calculate it by the deviations of the fluctuations. You build a mean value, you multiply it with the viscosity, and then you get your dissipation. So you see, viscosity is also part of the dissipation, and I think you already know this from your daily life. If you have a really fluid, really a fluid with really low viscosity, you get more swirls, but the dissipation will occur faster. And if you have a really high viscous medium, the dissipation will last longer. Yeah, you will have longer dissipation times. This is described here by this equation. And now it's getting more and more complicated. I see you will also have to solve an equation for the dissipation. Yeah, you have here your dissipation value, and again you have to solve the differential equation for this dissipation. You have to solve it for the rate of increase, for the convective term, for the diffusive term, and also for you will have a rate of production. You will can get more dissipation if you have more higher velocities, but you can also have a rate of destruction. That means also your dissipation will get smaller and smaller after time. Okay, and you see it's getting always, if some equations are too difficult, variables are introduced, and you have this C1 and C2 value, and you just use constant values for this C2s. Okay. Yeah. Now, if you want to recalculate the Reynolds stresses and you want to introduce this amount of turbulence, you want to, if you want to describe the change of momentum by turbulence, you can do it with this so-called turbulent viscosity. So this is a new variable introduced here in this system of equations, is so-called turbulent viscosity. And turbulent viscosity is calculated by energy divided by dissipation. And so it describes a new quantity here. And this will influence again your momentum equation. Yes, this turbulent viscosity has to be taken into account by your momentum equation. Okay, I don't want to explain here all these terms. Here you see it's conservation equation of the Reynolds stresses, and Reynolds stresses will be influenced by this so-called turbulent viscosity. Okay, and you see it's a pretty tough topic, and I just want to give you some advantages and disadvantages of this model. At first, why do we need this model? We need this K-epsilon model because we want to describe the swirls. We have to describe turbulence. If you imagine a hurricane in a weather forecast, or if you imagine a big swirl in the sea, you need to describe it. You cannot neglect it. Or if you want to fly with your airplane and there is a turbulence in front of you, you have to describe it. You cannot say I can't describe it, so I don't have to do it. You must describe it. And the advantages of this K-epsilon model for turbulence is that it is relatively simple to implement. You just need two additional conservation equations or two additional balances for these two quantities. Another advantage is that this model is quite really easy to implement, and it's a stable calculation. It converges relatively easy. So this is quite easy to do it. And it's also a really good model to predict and to describe many different types of flows. But it has some disadvantages. It is not so good for swirling and rotating flows and flows with strong separation. Axisymmetrical jets are difficult to describe. Also, it's only valid for fully turbulent flows. If you have regions where you are more laminar, it's not so good. And of course, it's a huge simplification. Normally you have different swirls in all the directions, and here you just concentrate it on one simple value or on two simple values. Okay. Okay, I just want to mention this. You can also have alternative models to this K epsilon model. There exists also a K omega model. maybe you can just test it in ANSYS. And this K omega model is really similar to the K epsilon model, but the K omega model is is better near to wall regions. And it's not the K epsilon model is more in the free flow field, is better in the free flow field and not so good in this near wall regions. Okay, here's a list of other models, alternative models. You can use many of them in ANSYS, you just switch them on. We can have here this K epsilon Reynolds stress model, the K epsilon realizable model. You can have K omega models. You also algebraic stress models exist, nonlinear models, and so-called large eddy simulations. And the simulations I've shown you from the gasoline filter, they were made with large eddy simulations. In large eddy simulations, you can predict the turbulence much better and much more realistic than in so-called K epsilon models. So you really see the fluctuations. Okay, here again is a list. I don't want to read it all, but here are some turbulence models summarized. The Spallard-Almaraz model, standard K epsilon models, this RNG K epsilon models, realizable K epsilon models, and also so-called Reynolds stress models. The advantages and the weakness of the different type of models. If you want to do this simulation and you want to do a good simulation, you have to choose the model really good to have good prediction. Okay. Here's also a small summary. You have your laminar boundary flow. You have your inlet. And here you get your turbulent swirls and the viscous subplane. That's again, if you're near to walls, some turbulence models are better, for example, K omega models. And if you're in the far flow field, other models have advantages. Here's again a picture with fluid flow through roughness of the pipes. There's also a D norm where you can estimate the roughness. Again, okay. I think I already explained this. Okay, Mr. Martin, we can stop the video here.